Hello and welcome everyone. My name is Shubhadeep and I am a part of Samsung Electronics. Almost a year back, my team got the project for verification of a particular audio IP. As we spent some time reading the specs, one thing we understood is that this IP is somewhat different from the other standard IPs like USB, PCIe or memory that our team had been verifying so far. Because we needed to do frequency domain analysis for this IP in order to properly verify its functionality. Now, most of you present here today might be familiar and working with Verilog, SV, or some sort of programming language for making your test benches. But how many of you have ever wondered on how to perform frequency domain analysis of your design's output in the same test bench? I, for instance, had no idea on how to do it and was naturally intrigued by a lot of questions at the beginning. As me and my teammates went exploring for the answers, we got to know the traditional approach for performing frequency domain analysis in the same verification setup. Today, I will discuss this approach and its drawbacks, and I will also present you with a new and better approach for dealing with this problem in a more seamless automated fashion. Hence, today our topic of discussion is verification of DSP-based audio IPs using a novel hybrid test bench architecture. Let us quickly look at today's agenda. First, I will introduce you to the audio IPs and the verification challenges that comes with it. Next, I will go to the implementation part where I will discuss our new technique for performing frequency domain analysis in conjunction with the traditional SV-UVM setup that we use for verifying most of the standard IPs nowadays. The next section will showcase you the results that we have obtained using our method, and finally, we will look at what we have achieved using our new technique and what else can be accomplished, what are the further scopes for this particular test bench. Let us quickly go through the introduction. When I say mixed signal audio IP designs, typical examples can be audio codecs, digital microphone interface, etc. And these are a part of the day-to-day electronics that we use like mobiles, televisions, laptops, etc. The main components of these audio IPs can be digital converters, filtering blocks, gain amplifiers, and there may be certain other signal processing blocks involved. For example, this particular duty has the digital processing blocks like ADC, gain block, filtering blocks, etc. And we are triggering this particular duty with an audio input which is analog in nature. And what we are getting is a sampled and quantized digital signal. Now comes the big question. Why do we need to do frequency domain analysis for this kind of IPs? Isn't our normal approach of scoreboarding enough? That is comparing input and output data bit by bit or frame by frame? I will explain why. It is because in these IPs, it is not just the normal data flow in standard IPs which involve functions like encoding, serialization, etc. These kind of IPs involve a lot of complex DSP algorithms sitting inside them, which makes it difficult to comprehend the input and output data bit by bit. Further, the different noises and group delays involved in the data path inside the duty makes it further difficult for matching the input and output data. So what are our alternatives here? One approach would be to design a golden reference model that will mimic our design functionality. But from a verification engineer's perspective, it becomes both difficult to design as well as time consuming. So the only solution left with us is frequency domain analysis. In frequency domain analysis, we will perform FFT or fast Fourier transform, which is a quick way to do discrete Fourier transform. So if you take this particular signal, which I discussed is the output coming from our duty, and perform FFT on it, we will get a waveform or signals which resembles this. And here the highest peak resembles the signal amplitude and signal frequency on the frequency scale, because this is a single tone signal, and the rest other components that you see on the frequency scale are the noises. Now When I do FFT like this, what I am actually doing is I am converting time domain data into frequency domain data. And this makes it a lot easier to analyze the design parameters like signal amplitude, signal frequency, noise, SNR, harmonic distortion, etc. Having discussed the why, now let us come to the how part. How are we going to do FFT in our traditional verification setup where most of us are using SV-UVM due to its obvious benefits like metric driven verification, flexibility, constant random stimulus generation, etc. But in spite of all these benefits, it comes with the shortcomings for our case, like it does not have a proven and widely used FFT library in System Verilog. Also, we don't have a way to plot FFT in System Verilog. So what is the solution here? The solution is to combine or club SV-UVM based test bench with another external utility like MATLAB, Python or C, which will be able to perform the FFT analysis for you. But also we need to make sure that the communication between the System Verilog and UVM based test bench with this external tool or utility should be automated. That is, you should not have to end your simulation in your test bench and again trigger this utility separately going inside the particular software or from your terminal. We should get rid of all that manual labor and the whole process should be automated. How this automation can be accomplished will be discussed in later with greater details. So first, let us look at the traditional method for FFT analysis. Now, industry-wide, generally MATLAB is taken as a standard tool for FFT analysis. Although a strong tool in itself, MATLAB licenses come at a cost. Hence, it creates a huge bottleneck in terms of licenses, particularly in situations where you are running regressions for testing multiple scenarios and configurations, which is a very basic need for any kind of verification work. And also in the developing phase of the test bench, where in order to reduce the workload or to quicken the process, you divide the workload between various engineers. There also less number of licenses creates a huge bottleneck. Also, the other popular languages like C, C++, etc. lack a widely accepted FFT library, which is also free for commercial usage. Now, let us come to our solution. So, we propose integrating SV-UVM based test bench with Python because Python has the biggest advantage that it is free and open source. And since there is no license constraints, we can run as many parallel simulations as we want to, which was not the case with MATLAB as we have seen. And Python is getting more and more community support and emerging as one of the most trending languages due to its features like readability, simplicity, OOP, etc. Results obtained using Python has also been cross-verified with MATLAB, and this gave us sufficient boost in our confidence that whether we use Python or MATLAB, we are going to get the same FFT results. So as you can see, this is the FFT calculated and plotted using MATLAB, and the same duty output when we gave it to our Python script or Python engine got the results that were similar to that of MATLAB. As you can see, the SNR and amplitude are both same for MATLAB and Python, and the waveform is also similar for both the cases. So we will encourage you to use Python instead of MATLAB because it does not have any license constraints. Now let us focus on one of the most difficult aspects of FFT analysis, which is the frequency leakage. So frequency leakage is nothing but the spreading of signal power across a range of frequencies, and it happens because the signal is not periodic in your sample time. So if you take this particular example, this is an ideal case where the signal is periodic within your sample time. That is, the starting and ending point on the amplitude scale is same for this signal. Now, when you perform FFT on this particular signal, what will happen is you will get a straight line on the frequency scale. So this will be your FFT when it is the ideal case. Now, when you are sampling in such a way that the signal is aperiodic in your sample time, like in this case, you will get an FFT where you will get a main lobe and there will be several side lobes beside it and surrounding noise components sitting after it. So when this happens, the net effect is that your amplitude goes a bit, your signal amplitude becomes a bit lower because signal power is being spread into the surrounding frequencies and your noise components become higher. So what you get is a lower signal amplitude as well as a lower signal to noise ratio. And the common causes for which this frequency leakage may take place is zero padding. That is, if you are taking 1000 points FFT, or if you are giving 1000 data points to your tool for calculating FFT, then the rest 24 points will be added by the tool as zero, that is zero padding. Because for FFT you need to have 2 to the power n number of data points, that is, for example, 1024 or 4096, etc. Also, if you are sampling your duty output signal in such a way that somehow within the sample time you are not able to sample complete number of cycles, then also this frequency leakage may take place. So we need to minimize this frequency leakage by devising some techniques. There are techniques like windowing techniques and coherent sampling techniques for this particular reason, which we will discuss later. Now let us come to the implementation part. So this is the hybrid test bench architecture that we have developed for this problem. And this is our SV-UVM based test bench, and this is the Python engine. This is our duty instantiation inside the test bench, and it is being programmed with tests and sequences. The duty, when triggered with audio signal coming from our audio driver, will generate the output signal, and this output signal is being dumped into a file, which is the data file. Also, we are putting some of the config parameters into another file as reference data for FFT calculation. These two data, that is the duty output and the reference data, are being taken by the Python engine for calculating FFT coefficients, which will be further passed on to other modules for calculating the audio parameters like amplitude, SNR, THD, etc. Finally, all the FFT results from the Python engine will come back to our SV-UVM test bench, where the monitor will employ checkers to validate the results. Let us take a look at the process flow. The first step is to configure the duty and generate stimulus. And when we are generating the stimulus, we also need to copy the input parameters into the input file. Next, we need to dump the duty output data into the data file. So all this part is happening in our standard SV-UVM test bench. Next comes the Python engine. Here, first we need to calculate FFT coefficients based on the above two files, that is the input file and data file. And the next part is calculating the other parameters using the same FFT coefficients. Finally, all these FFT results will be dumped into another file, which is the output file. And this output file will be read in the monitor of our SV-UVM test bench to validate the results. Let us start with the first part, that is the stimulus generation. While generating stimulus, we need to take care that there is no frequency leakage during FFT analysis, and also that there is no clipping of signal inside the duty. For that, we need to constrain our stimulus in such a fashion that we need to take care of the following three things. Firstly, the input sample size. Now the output sample size will be dependent on the input sample size. So we should choose the input sample size large enough that our output sample size is so large that it gives us a reliable FFT. And also the choice of frequency has to be chosen. We need to choose the frequency very carefully if we are going with the coherent sampling. We will discuss on the criteria of coherent sampling later in this presentation. And finally, the input amplitude and the gain programmed inside the duty also needs to be configured properly so that signal clipping does not happen inside the duty. Now that we have given the duty the input stimulus and the duty has produced the output, this output needs to be communicated to the Python engine so that it can calculate the FFT coefficients. So how is the test bench going to talk with the Python engine? So there are two approaches here. The first approach is that your SV-UVM based test bench talks with C language with the help of DPI, and then the C again talks with the Python engine with the help of a client server architecture. Now there is a lot of coding involved here in terms of the DPI infrastructure and the client server infrastructure, which is a very hectic thing to do for the verification engineer. So we suggest a much easier process, which is the file based approach. In this case, what we are doing is we are dumping the info file and data file from the SV-UVM test bench. The Python engine will read from these two files to calculate the FFT. And finally, the results from the Python engine will again dumped into an output file, which will be read by our test bench for validating the results. Now that we have devised a mechanism on the sharing data between the SV-UVM based test bench and the Python engine, we also need to make sure that the execution of the Python script happens automatically. We don't want to end our simulation and go into the terminal and fire the Python script, because that will cause us manual labor. And when you get the output from the Python script, again you need to come back with that output to your SV-UVM test bench manually. So we want to save all that manual labor. In order to automate this, what we have done is in the check phase of our UVM monitor, we have put this system function whereby the Python script will be executed automatically while taking this info file and data file as inputs. And finally, it will produce this output file as output from this script, which will again be read by the test bench for validating the output. Now let us see what kind of coding goes inside the Python engine. Firstly, we need to read the output channel recordings from the output file and ascertain its length. The length should be 2 to the power n, otherwise zero padding will happen and it will cause frequency leakage. The next step is to apply proper windowing technique. There are windows like Hamming window, etc. defined in the literature, and you need to find a proper window function which suits your particular application. Alternatively, if we can, we should go with the coherent sampling because it will give us the better result. But if we want to use coherent sampling, we need to constrain our input frequency such that it is a prime number multiple of frequency resolution. Frequency resolution is nothing but the sampling frequency divided by the total number of samples. And finally, after all this pre-processing is over, we need to apply the FFT using this particular function, that is numpy.fft.fft, which is a part of the numpy.fft library. And after we get the FFT coefficients, we will pass on these coefficients onto further Python modules for calculating signal to noise ratio and harmonic distortion. So this is a code snippet from our Python engine where we are using the same steps as I discussed in the last slide. As you can see, here we are calculating the FFT using the numpy.fft.fft function. The last part in the process flow is the checking of results. For this part, the UVM monitor reads data from the output file generated by the Python engine, and it employs checkers to validate the duty output signal, and it checks against the following parameters like amplitude, frequency, gain, filtering characteristics, signal to noise ratio, harmonic distortion, etc., and reports us whether these parameters are matching our expectations. Now let us come to the results that we have obtained using our test bench. So this is an oversampled sinusoid signal which is given as duty input, and it represents an analog signal because the sampling frequency of this particular signal is 1000 to 10,000 times higher or even more with respect to the sampling frequency of duty output. Next, what we see is the duty output, which is the quantized and sampled signal which comes from the duty, and this particular data points from this signal are dumped into the data file which goes into the Python engine. Now this particular waveform is plotted using Python from the data points that were present in the data file, and when we use those data points to calculate FFT, we get a graph like this. Now this particular FFT result, as you can see, has given us results which are not very good, like the SNR is only 23.81 dB and output amplitude is minus 2.41 dB. THD is also not very good. This is because we did not use any technique to reduce the frequency leakage. Now we will see what happens when we use windowing techniques to reduce frequency leakage. So here we have applied the Hanning window, and when we use it, we see there is a significant increase in SNR and output amplitude and harmonic distortion as well. When we use the same Hanning window but increase the total number of samples from 1024 to 4096, we see a further jump in SNR value and output amplitude. We have also used another windowing technique, that is the Hamming window, for experimental purpose, but the results were not as impressive as the Hanning window. So we thought that Hanning window was better suited for our particular application. Next, we see the another method, which is the coherent sampling. And in coherent sampling, as I had discussed earlier, your frequency should be constrained such that it is a prime number multiple of your frequency resolution. In this case, frequency resolution is 11.71875 Hertz. So in order to have a frequency which is closer to 1000 Hertz, which we had in the previous cases where we were applying the windowing technique, we had chose a prime number which is 89, so that it gave us a frequency like 1042.96875 Hertz, which is very much closer to the 1000 Hertz. And you can see that we have got SNR and output amplitude which are far better than the windowing technique. So if you can constrain your input frequency properly to the criteria of coherent sampling, you should always go with coherent sampling. And we have used the coherent sampling for analyzing multi-frequency inputs as well. So this is the output that we obtained when we triggered our duty with a multi-frequency signal which has two frequencies, and this is the FFT result. As you can see, we have the signal amplitudes in the frequency scale at around 1.6 kilohertz and 1.7 kilohertz respectively. So here is a comparison table which shows you the amplitude, SNR and harmonic distortion for the various techniques used, from the normal 1024.FFT where there were no techniques used, all the way to the coherent sampling technique with 4096.FFT, where we have got the best result in terms of all the above parameters. So I am towards the end of my discussion, where I have taken you through the various details of our proposed methodology. We have seen how we can easily build up an SV-UVM test bench which supports FFT analysis. This new technique which we have used for successfully verifying our audio IPs can be easily extended to other mixed signal IPs which involve complex DSP algorithms. And the results that we have obtained using our Hybrid-Testbench have also been verified against MATLAB to ensure that the Python results and the MATLAB results were in sync. Also, the Hybrid-Testbench has proven beneficial by supporting us with all the DV friendly features like automation, metric driven verification, randomization, stability, and ease of usage. Hence, I would encourage everyone to use this hybrid test bench for all the amazing features it has to offer. These are some of the references that we have used for our study. Thank you for your attention, and now I am open to questions and would try my best to answer them satisfactorily.